Okay, we're now going to talk about section 7.1, which is the introduction to sampling distributions. Sampling distributions is the theory that statistical inference is based on, and statistical inference is what we're going to be doing the rest of the year, chapters 8 through 12, and so it is sort of a theoretical thing, but it is one of the most misunderstood concepts in AP Stats as far as how it applies later on. I think during the chapter, most people tend to do pretty well on it, but really understanding it deeply is important because you have to see how it connects with making a confidence interval and doing a hypothesis test, which are the two big activities really that we're going to do the rest of the year in each of the chapters. And a lot of this stuff we've been talking about throughout the year, so I'm going to try to explain it right now. That 7.1 has the basic concepts as it relates to sampling distribution and basically just understanding what a sampling distribution is. The first concept is a population, and a population is just the whole group you want to know something about. So it is the whole group you want to know something about. And it could be anything. It could be any, people, animals, or things. Could be, every voter in the United States, or it could be every potato in this big truckload of potatoes, or it could be every student in a school, or every dog in this dog kennel. It's just a whole group you want to know something about. And then the parameter is what you want to know. A parameter is a value that describes the whole population. And most of the time, when the rest of the year, when we're talking about a parameter, we're going to either refer to a mean, which is mu, or a proportion, which is p. So those are the two most popular ones we are going to deal with. So you may want to know the mean test score of all these students in the school. So the population is all the students in the school, and mu is their average test score, their mean test score. Or we want to know a proportion, the proportion of students that pass the test. So now, of course, there's lots of parameters. We could want to know the standard deviation, which would be sigma. We could want to know the median, which really doesn't have a notation to it. Or we could the interquartile range, the range. I mean, there's a large number of parameters, but those are the two that we're most interested in. And if we wanted to know what those actual values were, we could survey everybody or everything in the population and find those values. In other words, do a census. But what we're going to do the rest of the year, most of the time, is we're going to take a sample. A sample is just a subset of the population. Subset of the population. And of course, the key thing is, how was the sample gotten? How did you come up with this subset that you're actually studying? And we want it to be gotten randomly. Anyway, and so what we'll do with the subset is we'll find a statistic, and that is just a value that describes a sample. So, and very typically, most of the time, it could be the mean of the sample, which would be x bar, which estimates mu, or it could be a proportion of the sample, so it could be p hat, which estimates p. So we want to know the mean test score of all the students in the school. We take, let's say, a sample of size 50 and find their mean. And so that mean would estimate mu. Or we want to know the proportion that passed the test. So we find the proportion our sample that passed the test, and so this p hat is going to estimate p. Now, there's lots of different statistics. We could come up with a sample standard deviation, which would be an S, or a sample median, or a sample range, and all those would be estimates of their corresponding parameters. But these are the big two that we care about. Now, what a sampling distribution is this, and here's the main thing. It is every value a sample statistic, which most of the time, like I said, is going to be an x bar or p hat. Every value sample statistic can take in repeated samples of the same size. In repeated samples of the same size. And so whenever we get an x bar or a p hat or any statistic, we're always saying to ourselves, This is just one of many that we could have gotten, and the other ones are going to almost certainly be different from this. But let me show you what I mean by that. So let's say, for instance, we are estimating some mean. So let's say we want to know, let's say our population is all of the trees in this forest. There's this large forest, and let's pretend, there's 20,000 trees in the entire forest. So that's our population number. Big N means the population size. And so let's just pretend that the average height of the trees is what we want to know. And let's just pretend that the average height of those trees is 31.7 feet. Now, very typically when we do sampling as we go through the year, we're not going to know what mu is. We're going to have to estimate it, but in this chapter, we're going to pretend like we know it so that we can create the theory that we can do our stuff with, okay? And so what a sampling distribution is this. We say, okay, I want to estimate mu, and so I'll take a sample of, let's say, 50 trees and find the mean of those 50. Now, the mean of those 50 is going to be an X bar. Okay, it is an estimate of mu, and it's probably going to be somewhere around mu as long as I've done this in an unbiased way. In other words, if I've randomly gotten those trees. And so it may be like 32.16 feet. Okay, and that is my sample value, but I realize when I get this sample, hey, it's probably going to be off from mu just by chance, what we call sampling variability. And as a matter of fact, if I take another sample, it's also going to vary then. So if I say, well, here's just my first sample, so I'll call it N sub 1 and X bar sub 1. If I take another sample, N sub 2, another sample of size 50, and I get X bar sub 2, and so, it may be 32.5 feet tall. And if I take another sample, N sub 3, a third sample of size 50, and find another X bar, it's also almost certainly going to be different. And so all these values are going to vary. It's not that I've done anything differently, so to speak. It's just that they're just going to be different just by chance. And so what's happening here, if I look at all the possible values of X bar, here's my mu, which in this case is 31.7. And so the X bar down here would be somewhere down here, in the 32.5, somewhere up here, in the 32.16 is somewhere right there or whatever. And if I kept finding X bars in repeated sampling, these X bars are going to vary just by sampling variability. And if I think about all the possible values of X bar in repeated sampling, theoretically, if I were to take an infinite number of samples, so to speak, all these values of X bar, this is what we call a sampling distribution. A sampling distribution is every value a statistic could possibly take. So in this case, every value that X bar could possibly take. And you'll notice what these X bars average to. They're going to average to the mu as long as I haven't have bias in some sort of way. So whenever we get an X bar, this is always coming into our mind. We say, well, this is the X bar I got in my sample, but I know it's just one of many I could have gotten. And all the ones that I could have gotten, that is what we call a sampling distribution. Not a sample distribution, but a sampling distribution. Every value a statistic could take in repeated sampling. And that concept is the basis of how we're going to make confidence intervals and how we're going to do hypothesis tests. Okay, and the other big situation we're going to have in sampling distributions is with proportions. So let's say if we want to know, we want to estimate the proportion of trees that have a fungus. And so once again, our population is just those 20,000 trees in the forest. And our parameter, which in real life, we won't know the parameter, but once again, we're just creating the theory to work with here. So in this chapter, we're going to pretend like we know the parameter. And so let's say, for instance, 21% of the trees, or 0.21 of the trees, have a particular fungus. And that's what we're trying to estimate. So we estimate it by taking a sample. Let's just pretend, for simplicity's sake, that I take a sample of size 100. Okay? And I'm trying to estimate the proportion of trees in the forest that have a fungus. And so I get X, my number of successes, so to speak, and let's say it's 24. And so my p hat would be 24 out of 100, and so it's 0.24. That is my estimate of my parameter. That is the statistic that I'm interested in here. And this are going to be different. Why? Because of sampling variability. I mean, they could be the same thing, but most of the time they're going to vary. All right. because I've got a random sample here. And if I get another sample, if this was just my first sample, so if I take n sub 2, another sample of 100, and my x sub 2, my number of successes, let's just say, it's 0.1, it's 19, like that. And so thus my p hat sub 2, my second sample, I get 19 out of 100. And so that's 0.19. And all these things are going to vary. All right, just because of sampling variability, and just like what I did up here with the x bars, these p hats are going to vary. And if I graph them all, they're going to be centered around the true population proportion. 21% of all of the trees, of all of the 20,000 trees, have the fungus. And if I take sample of size 100 and find p hats for each of them, this sample is like 0.24, which is up here, and this one's 0.19, which is there. And if I kept going on and made many, many samples, finding the proportion of trees in the sample that have the fungus, and I find all of these p hats, and I graph them, I am creating what is known as a sampling distribution. A sampling distribution is every value that my statistic could take in repeated sampling. Every value in this case that p hat could take in repeated sampling. If I did this a large number of times. And so whenever we get a sample statistic, a x bar or a p hat, or any of them for that matter, a sample standard deviation, a sample range, a sample median, we always say to ourselves, okay, here's the one I got in my sample, let's say. 0.24, and we're going to say to ourselves, it's just one of many I could have gotten if I had taken many different samples, but this is just one I could have gotten. And so the actual value of the parameter is probably going to be different from this, even if I had no bias at all. And so that is what sampling distributions are. It's every value a sample statistic could possibly take. Now, what does an unbiased estimator mean? Unbiased estimator means this. Notice that if I were to average these x bars, if I were to average these values, they would in fact equal to mu if it is an unbiased estimator. Unbiased estimator. Bias means if the average of my x bars was away from mu. And a similar thing here. What does an unbiased estimator mean? Well, it means the mean of my p hats is equal to p. Any of the individual p hats is almost certainly going to differ from p, but the average of the p hats is equal to p. Well, and so this would be unbiased. That is a picture of no bias going on when the mean of the p hats is equal to p. But just to give you an example of something that would be biased, let's say if I wanted to estimate let's say the proportion of people in a city that are Republican, that are a member of the Republican Party. And let's say the true parameter is 0.5, half the adults in the city are Republican. But I just went out and I hung out on the street corner in a real conservative part of town. And so my p hats that I could get are going to be up here, let's say around 0.7. And one of them I get 0.7 and 0.68 and 0.73 and so forth. So here's my p hats up here in my biased sample, because I'm hanging around in a place where there's a lot of Republicans, and I'm underrepresenting the liberal part of town, let's say. And so that is what bias looks like. Bias is when the mean of your statistics is not equal to your statistic. Okay, I mean, it's not equal to your parameter, rather. Sorry. Now, granted, one of the p hats, it could happen just by chance that one of the p hats is like really close down here. But bias isn't when just one of the p hats, but it's when the average of all the possible p hats is like that. And a similar thing with the x bars and with the mu. And so, and what is an unbiased estimator? An unbiased estimator is when the mean of the statistic, that being x bar or p hat, in repeated sampling equals the parameter. And these two little formulas are on your formula sheet. That in other words, the mean of your x bars is going to equal mu, and the mean of your p hats is going to equal to p. As a matter of fact, I'll go ahead and show it to you. So on your formula sheet, here's the formulas for this chapter. Of course, this is going back to binomial in that last chapter we did, chapter 6. But notice the mean of the p hats is equal to p. the mean of the x bars is equal to mu. And there's the formulas for the standard deviations, which we're going to get into in future sections. But so that's what an unbiased estimator is. And then a couple of important concepts I want to talk about here. What is high and low bias, and what is high and low variability? And we'll go with a mean example here. And so let's say, for instance, I'm trying to estimate some mu by taking x bars. So if we have low bias and low variability. So low bias, we've done a good job of getting a random sample and doing everything in a nice unbiased way. And so my x bars, they'll vary from you just by sampling variability. Not that you're doing anything wrong, just by random chance. And so, but in a low bias, low variability situation, these things really stack up. And the x bars, first of all, the mean of the x bars appears to be equal mu, so that's low bias. But low variability means they're kind of wadded close. They aren't spread out much. Where if you have this, let's say if you have low bias and high variability. So that would be a situation like this. So here's my mu, but my x bars are spread out like that. Typically, this is what happens when you have a small sample size. Small sample size isn't going to create bias. It's going to create a lot of variability. So we don't have bias here because the mean of my x bars appears to be roughly equal to mu. Okay, it's roughly equal to mu, but they're spread out a lot. And so typically, like I said, that is when you have a small sample size. Now, let's say if you have this, let's say if you have high bias, and low variability. High bias and low variability. So let's say here's the mu that I'm trying to estimate, and I consistently get x bars that are too high, kind of like that example that I talked about a minute ago in regards to the Republicans. I have very little variability. In other words, I have a big sample size, all right, that's producing a lot of precision, so to speak, but I'm zeroing in on the wrong number. So that would be high bias. The mean of my x bars, is not equal to mu. And so that not equal to mu. So that's what bias looks like. But low variability, they're close together. And lastly, we have a situation where we have high bias and high variability. So the average of these x bars is away from mu. So I have my x bars, and the x bars are really spread out. So this situation, I've got like a really small sample size, and I'm doing things in a biased way. I'm not getting a random sample. I'm doing something like a convenient sample or a volunteer response sample or some sort of survey with poor question wording or some sort of bad data collection. So the mean of my x bars is not going to equal mu, and they're really spread out. And so that's sort of a popular question in regards to sampling variability or sampling distributions. And then lastly, one of the biggest mistakes people make is getting the terms population distribution, sample distribution, and sampling distribution mixed up. First of all, a distribution is in essence a list of numbers, is what it is. So, your population is the whole group you want to know something about. And the population distribution is everybody's number, okay, or everything, like in going back to the tree example. So it would be the heights of all of the trees. So it's every number in the population. So the population distribution is every value in the population. So in our tree example, in other words, it would be the heights of all of the 20,000 trees in the forest. So it'd be those 20,000 numbers. That's the population distribution. So in our sample there, we said we took a sample of size 50. So our sample size is 50, let's say. We have 50 trees. And so it is, the sample distributions, in a distribution is a list of numbers. So it is in essence every value in the sample. Every value in the sample. So, in other words, in this case, it is the heights of the 50 trees in the sample. So it is the numbers you're actually working with, because you're not going to go measure all 20,000 of those trees. You're just measuring these 50 trees and using that X bar to estimate that. So that is the sample distribution. And that is very different from the sampling distribution, which is what we've been talking about up here. The sampling distribution, once again, the sampling distribution, very different from the sample distribution. It is every value. The statistic, which in this case is X bar, can take in repeated sampling. If we were to do this again and again and again with samples of size 50, and not just find one sample of size 50, but find many of them, so that would be the sampling distribution. Okay, thanks for watching the video, and I hope it was helpful.